Earlier you learned about the standard error of a statistic. Now we're actually going to use that as a way to measure strength of evidence using something called a standardized statistic. So we're going to look at this in an example about NFL overtime rules. So between 1974 and 2009, overtime in the NFL started with a coin flip to decide which team would get the ball first in overtime, and then the team that scored first was declared the winner. They changed the rules in 2009, and that was because fans and players thought these rules were unfair to the team that lost the coin flip. And we can actually look at data on this. Between 1974 and 2009, there were 428 games that went to overtime, and 240 of the games were won by the same team that won the coin flip. So does this provide strong evidence that winning the coin flip is an advantage? All right, so let's formally carry out the test. So the parameter is going to be the long-run proportion of games won by the team who won the coin toss, right? What would happen if the NFL played with this rule forever and ever? What would the proportion be? The sample proportion that we're going to use to estimate that is our p hat, and that's going to be 240 out of 428, which is 0.5607. So I'm curious what your intuition is. Do you think that this is going to provide strong evidence that winning the coin flip is an advantage? What do you think? Okay, so let's state our hypotheses. So hypotheses are always going to be stated in terms of the long-run parameter, right? That's what we really care about. And the null hypothesis always has an equal sign in it. So in this case, the thing that we're sort of testing is whether or not the rule is fair. So if the rule is fair, then the long-run proportion of games won by the team who won the coin flip should be 0.5. So the null hypothesis is that the rule is fair. And if we look at the way the question is phrased, it says, does it provide strong evidence that winning the coin flip is an advantage? So our alternative hypothesis is going to be that pi is greater than 0.5. Which would mean that winning the coin flip is an advantage. So in other words, the team that wins the coin flip goes on to win the game more than half the time, right? And that shouldn't happen because with the coin flip, the quote better team should win the coin flip half the time since it's random. So you would hope that there wouldn't be any correspondence between the team that wins the coin flip and the team that wins the game. So what we really need to know is this sample proportion, 0.5607, it's higher than 0.5, but is it high enough to be convincing, right? Is this the kind of value that would happen just by random chance alone in this particular set of games? So we already know one way that we can answer this question is to calculate a p-value. But here we're going to do something a little different. We're going to calculate a Z-statistic. This is also called a standardized statistic. And we'll see why in just a second. Okay, so to calculate a Z-statistic, you're going to start off with your regular statistic, which in this case would be 0.5607. That's our sample proportion that we're going to use. Then you're going to subtract the null hypothesis value, right? So by doing this, we're really looking to see how far is our statistic, the thing that really happened, from what we would have expected if the rule were fair. So here we see that the difference comes out to be 0.0607. But is that a big deal? Is that enough to be convincing? It's sort of hard to tell just by looking at that. So instead we're going to standardize by putting it in terms of the standard error. So I'm going to go back up here. We had this sample size of 428 looking at the coin flips, and we got the value for the standard error here was 0.024. So I'm going to fill in that standard error into the formula for my Z-statistic. So now I'm not just looking at the distance between what really happened and what we expected under the null. I'm looking at the distance in terms of the standard error. So when I calculate this, I get 2.529. And we can interpret that by saying that our statistic, 0.5607, is about 2.529 standard errors, and it's higher, it's a positive number, so it's 2.529 standard errors above what we would have expected if the rule were fair, if the null hypothesis is true. Right, so this is another way of saying how extreme is this value. And we can go ahead and draw this on the graph. Let's find our sample proportion, 0.5607, and you can see it's pretty far out there, right? This is pretty unusual. So we wouldn't expect to see data like this if the rule were actually fair. So this 2.5 standard errors from the center, this is a pretty extreme value. What if we had tried to do this based on only 10 games? So let's say that we looked at a set of 10 games, and 6 out of 10 times the team that won the coin flip went on to win the game. So p hat equals 0.6. So in this case, p hat is larger. So does that provide stronger evidence that the overtime rule is unfair? Intuitively, no, right? It's going to be very difficult to say anything based on a set of only 10 games, but we can confirm this looking at the Z-statistic. So when we find the numerator, the difference between 0.6 and 0.5 is actually bigger than it was before. But the standard error is going to be bigger too, right? If we come back up here and we look at the standard error when the sample size was 10, the standard error in that case was 0.158. So I'm going to fill in 0.158, and this ends up giving me a Z-statistic of only 0.633. So in this case, the statistic is 0.633 standard errors above what we would have expected if the null hypothesis were true. And if we find this on our graph here, here's our 0.6, p hat equals 0.6 is not unusual, right? It would be very common, even if the rule were fair, to see 6 out of 10 times that the team that won the coin flip won the game. So in this case, with the smaller Z-statistic, we're going to have weaker evidence, right? We're not nearly as sure that there's a real problem with the rule based on this 6 out of 10 as we were with the real data. So this is how it works in general. As the evidence against the null hypothesis gets stronger, the standardized statistic gets further from zero. So basically, this is a way of measuring how far is your sample proportion away from what you expected it to be, either above or below, in terms of the standard error. So just like with the p-value, our book provides some guidelines for deciding how strong your evidence is. And kind of the same as p-values, I'm not super duper attached to these. There's actually even some times where the guidelines for p-values and the guidelines for standardized statistics contradict each other. But still, it's good to have like a general sense of how far from zero your standardized statistic needs to be before you have strong evidence. So the guidelines in the book say if it's between -1.5 and 1.5, that's weak evidence. If it's below -1.5 or above 1.5, that's moderate evidence. Below -2 or above 2 is strong, and below -3 or above 3 is very strong, so always against the null hypothesis. So in this case where we had a Z-statistic of 2.529, this provides strong evidence against the null. So this gives us strong evidence that the overtime rule that the NFL was using actually did provide an advantage to the team who won the coin flip. So it's good that they stopped using that.